Thank you. Yeah, so we've been doing some research on modular categories, and as part of that, we decided to investigate the representations of SL2 Z mod in Z, and we've done a bunch of calculations and work on that. So I thought I'd introduce that and go over some of the examples. So first off, I just introduce what a modular category is in very rough terms. So it's an abelian C-linear category, and then it has a whole list of additional structures on it, but very roughly, it's a fusion category, which means that it's semi-simple, and we have this multiplication on the objects, and that this essentially works sort of like fusion of quantum particles, with the simple objects taking the place of the types of particles in the system. And secondly, it's a ribbon category, which means that we have a braiding and twists and duals and things like that, which essentially mean that the morphisms in our category act in a topological way. So again, our objects are taking are sort of acting as the particles in a quantum system, and the morphisms act as those particles moving around and twisting around each other and things like that. And finally, we call it a modular category if we define this matrix called the S matrix, which is formed of this hop-link kind of morphism. And if the matrix we get from that is non-degenerate, then we call the category modular for a reason I'll explain in a few minutes. Okay, is that clear? Okay. So that's the S matrix. The other kind of matrix I'm going to talk about a lot today is the T matrix, which it consists of the twists for the category. So our twists are defined according to this twist shape here. And if I is a simple object, then we can express the twist simply as a complex number, because this is going to be a scalar. Okay, and the S and T matrices together, we call them modular data associated to our modular category. So modular categories show up in a bunch of different areas in math and physics, but a couple examples. So if we have a modular category, we can use the information in that category to construct a 2+1 topological quantum field theory. And we can then use that for a bunch of different things. For instance, we have what's called a Levin-Wynn model, which is a model for describing topological phases of matter in quantum physics. And that can then be extended to create quantum error correcting codes, the most well-known of which is Kitaev's toric code. And in math terms, we can construct modular categories from a bunch of more simple algebraic objects, such as Hopf algebras. For instance, we can construct a modular category as the dual of any finite abelian group. And for certain vertex operator algebras with certain properties, you can also take their representation theory and get a modular tensor category that way as well. Okay. So a simple example of a modular category, which might be familiar from physics, is the Semion category. In the Semion category, we only have two simple objects. The one here just corresponds to the vacuum, and we have a single Semion called S. The T matrix here gives the twists of these two objects. And in particular, you notice that the twist of the Semion is I because it has spin 1/2. And then the S matrix, as we defined before, looks like this. Okay. All right, any questions so far? All right, so the reason we call the S and T matrix the modular data is because given these S and T matrices associated with a modular category, we can always get a projective representation of SL2Z. And we define it simply using these S and T matrices. I'm using S inverse in this case just because of a sort of notational difference between the way we define S and the way it's defined by other people. And since this gives us a projective representation, we can always lift this to a linear representation. We just have to normalize our S and T. And we usually write that with a lowercase s and t after normalization. Okay. So this gives us a nice representation of SL2Z. And one of the big questions we might ask about this is whether a given representation of SL2Z is actually comes from some modular category that we can find. This is in general an open question. We know it about a couple of representations, but for maybe the majority of them, we don't actually know. Okay. It's worth noting here, I say some lift because given a modular category, there are in general several lifts. In fact, there are 12 different lifts of its projective representation that give us actual representations. So the thing that we in particular were working with here, and the reason why we decided to investigate these representations, is that we're trying to classify the semi-regular categories. So let me define what a semi-regular category is. So if I have a modular category, I can define this number field Q adjoin S, which is just Q adjoin all of the elements of its S matrix, okay? And it can be, so this gives us a finite extension of Q, and then we can look at the Galois group of that extension. And if we take an element of the Galois group, well, it has to send every simple object to some other simple object, possibly the same simple object, which gives us a permutation of the simple objects. And so using that, we can define this action of the Galois group on the simple objects, okay?
Before you go on, let me jump in here with a question. Do you know that that's a Galois extension? Or you take
yes.
the Galois closure of that field?
Yeah, because, no, it's always a, well, I guess you have to take the Galois closure just because it's just a, so Q adjoin S is contained in Q adjoin T, and the T matrix consists of nothing but roots of unity. And so Q adjoin T is just Q adjoin some cyclotomic number of appropriate order. And then Q adjoin S may be slightly smaller than Q adjoin T, but it's always just a cyclotomic extension.
Okay.
Yeah, does that help?
Yeah.
Okay. All right, so then basically we just look at that permutation and we call the category semi-regular if the permutation that we get is semi-regular. That is, if every object has a trivial stabilizer, which in effect means that the action consists of a number of orbits all of the same size. And so in particular, if it's one semi-regular, well, that means that the orbit is transitive. So such categories are called transitive, and Dr. Ng and Dr. Wang and Dr. Zhang classified these completely, finishing last summer. So now we're looking at the two semi-regular categories. That is where we have exactly two orbits, and you can prove that they're the same size. So let's look at a two semi-regular category. So perhaps the most useful property for classifying this is that if two objects lie in the same Galois orbit of a two semi-regular category, actually if an n semi-regular category for any n, then the orders of their t values, their t values have the same order as roots of unity. So in this case, we're looking at a two semi-regular category. That means we have at most two distinct orders. Okay. And one of the things that we proved so far is that if the two orders are in fact distinct, then we can describe the category pretty precisely. It's exactly the Deligne product of two Fibonacci categories. and then a transitive category. And since the transitive categories are already classified, this classifies them completely. So is that clear so far? Any questions?
Maybe you can give more details on Fibonacci categories.
Okay, so Fibonacci categories, if we look back at this Semion category, they're kind of similar. Again, the Semion category here is rank 2. So it just has 2 simple objects, and Fibonacci categories are also categories of rank 2. Does that help? There.
Yeah, you can say what's special, why it's called Fibonacci.
Oh, well, the data associated with, I think, particularly the F values for the fusion are basically give rise to the Fibonacci numbers. That's, yeah. Okay.
Okay.
Yeah. Okay. So let's talk about, so the way that we figured this out essentially was using this fact about the orders of the T matrix. So it's very useful to know precisely which kinds of representations we can find for such categories. And in particular, if we know the representation, then we can figure out what orders of T we can get. So to construct such a representation, suppose that I'm looking at a particular modular category, then there's this proposition that any lift of that projective representation factors through SL2 Z mod NZ for a finite n. And we call that n the level of the representation. Okay. And in fact, we can say precisely what the level, we can give a precise bound for the level. It only goes up to the order of T or 2 times the order of T. Okay. So yeah, we're going to try and construct all of the representations of that type. Now, our level in general could be any finite number, but by using the Chinese remainder theorem, we can always decompose it into a bunch of irreducibles of prime power order. So that's what we're going to look for in particular. So we want irreducible representations of SL2 Z mod NZ, where n is a prime power. Okay. And it turns out that we can construct these using Weil representations. So to construct a Weil representation,
Weil representations, not Weil representations.
Sorry.
There is a mathematician, Weil.
I know.
W-Weil.
Yes. Weil representations, sorry. Anyway, so yes, we can start off by constructing a quadratic module. And we're in particular going to look for a quadratic form. And our quadratic form here is basically going to correspond to the S matrix that we had before, okay? You'll see when I do the construction later on. Okay. And so in particular, we're going to make a quadratic form. So it needs to have these properties, Q negative X equals Q of X. And then from the quadratic form, we also get a bilinear map B. Okay. And if any quadratic module corresponds to a pointed modular category defined by M. Okay. And you can see that the twists of such a category are given by our quadratic form Q.
So what does a pointed modular category mean?
So that's a modular category with a particular unit object, right? A specified unit object.
No, it's a pointed modular category is where every object has an inverse, so that you tensor these two, you get the unit object.
Okay. Yes. Yeah. All right. Okay. So, all right. So having constructed our quadratic module, we can then use it to construct a projective representation, W of MQ. And you can see here that W of MQ of T is defined by our Q of X, and WMQ of S is defined by our bilinear form B. And we construct this as a representation on the space of complex valued functions on M. Okay. So the key theorem here is that if we construct this representation of certain three types D, N, and R, which I'll describe in a moment, then our representation isn't just projective, but in fact an honest linear representation. And we can give it a specific prime power level p to the lambda. And furthermore, every irreducible representation of level p to the lambda shows up inside one of those three types, either as a subrepresentation or occasionally as the tensor product of two subrepresentations thereof. Okay. All right. Any questions so far? Okay. So the three types we're going to need, the first one is type D. And for type D, we're going to build it on top of this module Z mod P lambda Z plus Z mod P lambda Z. And our bilinear form is just defined by XY. And secondly, we have type N, which is pretty similar. The module is the same, but we define a different quadratic form on it, x squared plus xy plus 1 plus u over 4 y squared. And those quadratic modules essentially just come from the norms defined on certain number fields. This norm right here, the x squared plus xy plus 1 plus u over 4 y squared, it can be written in a slightly different form, but this one happens to be convenient for the calculations. Okay. And then, so those two types are relatively simple and uniform in how they behave. The third type is type R, which unfortunately is a little bit more complicated. So type R lambda sigma, in this case, our module is Z mod P lambda Z plus Z mod P lambda minus sigma Z. So it's not symmetrical. We have two different sizes for the coordinates. And in this case, the quadratic form is R times x squared plus P sigma Ty squared. Okay. And in this case, we have slightly different behavior if we choose P equals 2. So in that case, we get a different set of modules. And in that case, it's far more likely that we'll get sort of unusual cases where we need to split our subrepresentations further or take tensor products or things like that. So there are lots of small cases for our lambda sigma with P equals 2.
Before going on, let me make sure I understand what you're saying. You're saying every representation of SL2, Z mod P to the lambda for any lambda, is embeddable in one of these veil representations, or we want to call veil representations.
Yes, except in a very small number of cases where it doesn't embed in one of them, it embeds in the tensor product of two of them. But almost all of them embed in one. Yeah. Okay,
I'm just asking. So this is you're describing in some sense all the ways to get representations of SL2 Z mod P to the lambda in a certain.
Yeah, that's right.
Okay.
Yeah. Okay. All right. So the method by which we do this is by decomposing it. And so if we consider a representation of one of those three types and we look at its group of automorphisms, then we have this proposition by Klosterman. So if we take an abelian subgroup of the automorphisms, then we can decompose it into the character subspaces. Okay, and we call the that subrepresentation W of MQ chi. And then, of course, we can write W just as the sum of these character subspaces. And we're going to look in particular at what we call the primitive characters. And the definition of primitive here is that we have some element that leaves PM fixed pointwise. So that's just this submodule of M. And our character is primitive if it acts non-trivially on some such element. This definition is a little different from the normal definition of primitive, which has to do with conductors. It's just that it doesn't factor through any smaller group, but this is basically the translation of that into this case. And the big theorem by Nobs and Wolfart that we use to construct all of these representations is that if we look at primitive characters that don't square to 1, so they're of order greater than 2, then WMQ chi is in fact irreducible, and it has the same level as WMQ, which, remember, we could construct WMQ to have a level of a specific p to the power lambda. And secondly, they're all distinct unless we are looking at exactly the same module and exactly the same character up to conjugation. Okay. If you look at
go back and remind us what this group frac A is.
Well, so at this point, frac A could just be any abelian subgroup of OT MQ, so that this holds here. But in general, when we take when we're looking, we're going to take OT MQ to be just the elements of norm 1. But it depends on precisely which case you're doing. Usually, it's just the set of elements of norm 1 acting on MQ by multiplication. Okay. All right. Any questions so far?
So what is the notation, like you have, so like frac A was the subgroup. What does it mean with like the frac A with the hat on top?
Oh, that's the set of characters of A.
Okay.
So,
Okay.
yeah. All right. So then using that decomposition method, the theorem here is that with the exception of these 18 exceptional representations, every single irreducible representation of SL2 Z mod P lambda Z shows up inside one of our Weyl representations here, okay? And the 18 representations that are exceptions simply show up inside the tensor product of 2 of them. Okay. So almost or most of them show up in exactly the case described by the previous theorem, where our character is primitive and not of order 2. But there are those 18 exceptional ones and a number of, I guess, partly exceptional cases where we just have to take possibly characters that are not primitive or characters that do square to 1 or something like that in order to construct them. Okay. So I figured I'd go ahead and show you an example of such a construction. So let's look in particular at type N lambda chi. Okay, and we'll particularly take chi to be a primitive character, not squaring to 1. And if you recall from before, my definition of the module is that it's Z mod P lambda Z plus Z mod P lambda Z. So we can just think of it as a 2-dimensional space. Okay. And we define this norm, x squared plus xy plus 1 plus u over 4 y squared. Okay. And as I mentioned, this is a norm specifically associated to a number field, because we can think of M as being equivalent to Q adjoin square root of 1 plus u over 4. Okay. or square root of 1 minus u. Okay. And then we have a trace 2x plus y. Okay. And we had our quadratic form simply defined by the norm. And you can see that this is going to be of level p lambda, because remember that my twists are of e to this q here. In this case, as I said, was usually the case, we're going to define our group A to be just the elements of M that have norm 1. And we're going to treat it as a subgroup of the automorphisms simply by acting on M by multiplication. So what we need to do is construct a system of representatives for the orbits of A. And they're going to help us describe the basis for the subrepresentation we're looking for. In this case, we can construct a basis using these functions f chi of xy. And these are just defined by as a character sum here. Okay, so it's chi of CD times delta CD acting on xy. Okay. Now the reason we bring these up is that an element of that type automatically satisfies that original definition of the decomposition. Okay. And so we know that it automatically lies within V chi. Okay. And it turns out that in this case, as in most of the cases, elements of that type form a very nice basis for V chi. This is also why we want chi to be primitive, and we want it to not square to 1, because if those things occur, if it's non-primitive or if it does square to 1, then these V chi's can in fact turn out to be 0, which makes our basis a lot harder to define. We often have to have like sums of f's and things like that. Any questions about that so far? All right. And then given that basis, we can now calculate precisely what our values for t and s are. And as I mentioned before, the value for t is just given by the norm. Remember, that was the q that we had. And the value for s is equal to this trace of CD xy conjugate of y wz, but that is actually the b that we described before. Okay. All right, any questions so far? All right, so this allows us to calculate explicitly the T and S matrices that correspond to this representation. So in particular, we can construct one like this. This is type N3 chi minus. So in this case, I'm taking P equal to 2. And since P is equal to 2, and the chi that I'm looking at is defined by chi of 5, 0 equals minus 1, and chi of 0, 1 equals 1, that squares to 1. This is actually a primitive character, but it is of order 2. So in this case, that's why I have to look at N3 chi minus. I have to decompose my subrepresentation an additional time. Okay, and in this case, I'm just looking at the -1 eigenspace of a certain order 2 operator called kappa. Okay. And so what I get from that is 2 basis elements, F11 and F13. And then using just the formulas on the previous page, I can calculate the T and S matrices associated to them, which you might recognize correspond to the Semion category that I described at the beginning. Okay, so you'll note there's that zeta to the 5th there. Remember, I had to normalize the T and S matrices, so that's why it's off by a single scalar. Okay. So this case in particular is obviously realizable because we know exactly what category corresponds to this representation. Okay. On the other hand, here's a slightly more complicated one. This is type N2 chi. this case, we have P equals 3, so this is of level 9, 3 squared. So here we're taking chi to be defined by chi of 4, 3 equals zeta cubed. So that's a character that is primitive and does not square to 1. So this is sort of the normal case, defined precisely by that first theorem that I gave. So in this case, we just construct the basis as described before. Our basis in this case is these 6 elements. Remember that the indices of those bases correspond to orbits for the A, or the group A. Okay. And then my T and S matrices look like this. And we can show, Elong actually calculated that this matrix is not in fact realizable by basically trying to find which would be the unit object. And if you test all of them, it turns out that you never get a viable category from this. So this is a non-realizable representation. Okay. All right. So do we have any questions about those?
So maybe you can talk a little bit about some criterion that we know about admissible or realizable representation.
Yeah, so for instance, you can't really use it on this one, but the easiest criterion that we use a couple times is that the dimensions of objects in a modular category can never be 0. Okay, and if you write the S matrix in the proper form, such that the unit object, you pick out the row associating to the unit object, and you scale it appropriately, then the dimensions are simply found on the row corresponding to the unit object. So if you can show that the S matrix you found has the property that no matter how you choose the unit object and how you scale it and so on, you will always get a 0 on every row, well, then such a matrix can't be realizable, because you would inevitably have an element with dimension 0, and that can't occur. Okay. Does that help? Yeah. Okay. Another thing you might notice about this one in particular, which is common for, which is always the case for type N, is that in my T matrix here, all of my entries for my T matrix have the same order. They're all of order 9. So, for instance, I could then say that this can't come, at least directly, from a 2 semi-regular category with distinct orders, because there's only one order here. Okay, so that's the sort of logic we use for that. All right. So any other questions?
I have a question that sort of goes back to towards the beginning of your talk, where you had, when you were first defining your S and T matrices, and you used a sort of graphical, a picture, the loops and the twists. I was wondering if you could expand on what that notation means.
Yeah, so essentially the way you think of these pictures is that we're drawing we're trying to sort of draw what the morphisms represent. So it's a representation of graphical representation of a morphism. And in this case, I always read them from the top to the bottom. So if you look at this picture, actually, it's probably easier to describe it if you think about it at this one, okay? So at this time, I have this one sort of strand labeled with I. So I can think of that as a morphism from I to I. So it's an element of HOM II. In this case, I'm starting with an I. The cap here represents the creation morphism from 1 to I tensor I star. And then I apply the braiding on the right. That's what the crossing represents. And then I apply the evaluation morphism, which is the cup. And then I'm back to I. And so you're basically just reading down, and each symbol corresponds to a particular morphism, and they're just composed into a single morphism. Does that sort of help describe what's going on here?
A little bit. Is there anywhere you would suggest like that I could read and sort of get a grasp of this? Because I've never seen this sort of notation before.
Yeah, the book that I learned it out of was by Bakalov and Kirilov. Describes this graphical calculus a lot. But yeah, any book you might look up that describes modular tensor categories is going to have at least some sort of introduction to this. Yeah, but in particular, like I said, the sort of idea behind these is that we're thinking about this as, or they sort of correspond to the physical motion of particles. Okay, so if you think about this as the motion of a particle, this is a particle kind of turning around, right? And so that's why we call it the twist, and it corresponds to the spin in quantum physics, because it's a particle being spun around. And similarly, the S matrix here, well, this is a thing with these braidings and creation and evaluation morphisms. But if you think about it physically, this is two particles being created, the middle ones crossing around each other, and then they annihilate again. And so, yeah, does that help?
Like in a world line model?
Say again?
Like in a world line?
Yes, yeah, that's yeah. It's exactly the word lines. Yeah.
What did you mean by ear? That category? Sorry, I missed the beginning.
By which?
So I's and J's are morphisms, yes?
No. The I's and J's are objects in my category here. So what
by
I'm
the ears, just mean the simple objects?
Yeah, simple objects. Yes.
I see.
You can define this S matrix or this S morphism for any two objects, but what we're constructing here is the matrix based on the simple objects in specific. Yeah. The T matrix here, you notice this twist right here. Again, I could define this morphism for any object I, but the nice thing is that if I is simple, then I know Hom from I to I, because it's a simple object. Shor's lemma says that Hom I is just isomorphic to C. It's just the base field. And so in that case, then this morphism must in fact just be some scalar multiple of the identity. So that's where I get this theta I.
I see. Thanks.
Mm-hmm.
Also, is there notions of locality, or is this all local? Is this just a big local picture if you want to interpret it in terms of geometry or physics? Or because I know usually when you take a trace of these braiding diagrams or something like that, you're usually connecting something, and I don't know what would that mean in terms of these things.
So the way we take the trace for these diagrams is you actually just connect, and you connect a loop from the top to the bottom. Yeah. But essentially, when I talked about these topological properties, about this being ribbon, the topological properties are essentially that you can manipulate these morphisms as though they were, in fact, like not diagrams. You can move these things around in topological ways, and it'll still represent the same morphism. Does that make sense? So for instance, one of the properties is sphericality, which means that I could take one of these loops, and I imagine this is being projected on a sphere, so I can take that loop and wrap it all the way around to the other side and end up with a different looking picture, but it represents the same morphism. Mm-hmm. So yeah, they sort of correspond to strings or braids in a topological space.
Right. Thanks.
Mm-hmm. Any other questions?
So any other questions or comments?
Well, just one question. You have these, if you fix a prime number P, mm-hmm. and you take different lambdas, like lambdas 1, lambdas 2, lambdas 3, is there any mm-hmm. sense in which these things can fit together in a coherent way. Now, I'm not sure what that, this is a little vague what I'm asking. Because
Yes.
Theory of representations of p-adic groups.
Mm-hmm.
I don't know if this might be off the wall here, but you know, you have SL2 of the p-adic integers.
Mm-hmm.
And you have a notion of admissible representations of these kinds of p-adic groups. But I don't know if this fits into your, I don't know if there's a way to fit this into, have you thought about anything like that? Or maybe.
Yeah, but what I understand is that, and I apologize if I'm saying this incorrectly or something like that, but if you have a representation of Z mod, or of SL2 of the p-adic integers, then you can think of that, or it corresponds to a set of representations of Z mod P lambda Z for each, like for all lambda in Z. So that means you have a representation of Z mod PZ and a representation of Z mod P lambda 2Z and Z mod P3Z and so on. I think that's what it was. I haven't read about this specifically, but I remember this being mentioned because actually the paper that we that I mentioned with Nobes and Wolfart, that was actually specifically what they were investigating was representations of SL2 on p-adic number integers.
So you're saying some sort of limit?
Yeah, it's something like the limit of.
Is it like profinite or anything like that?
I don't know.
Yeah, I mean it's a profinite thing. But here's another question: if you take a group like SL2 of just Z P, there's a standard theory of that representation. You have what are called discrete series representations. You have these Deligne-Lustig characters. There's a standard way in which you build up the representation theory of any, well, we would say reductive Lie group over a finite field. But you can just take Z mod P, and there's a standard representation, you know, there's a standard way in which the character table of that thing is built up. Okay. So again, a dumb question. How do your representations fit into that picture?
So so they would be included in the list that we have constructed, but of course, the key problem here is choosing the basis. And so the basis that we have used to construct these is almost certainly not the basis that you would want for the standard representations. The basis we use here is based on those type D, N, and R, the quadratic modules that we constructed them from. So you'd have to figure out the appropriate base change matrix to get it into whatever present.
Right, I understand what you're saying. Of course, the way in which you construct these representations is totally different. But there is a classification of these guys. The representations of SL2 over a finite field in general. There's a standard way in which you build up the character table. And so it's just natural to ask, well, okay, you've got your representations and you have sort of the standard character, you know, the standard representations. Well, what's the relation between them? That's just the question.
Yeah, I mean, they should be included.
There must be some relation. I mean, there has to be. You've got representations, they've got representations.
Yeah, I mean, they should be the same. They're just different descriptions of the same thing.
Right.
How about the ramification theory? I didn't, maybe you said something about it at the beginning, but I mean, you said something about spherical. Usually it's understood to be like unramified.
Yeah, you're right.
So what about these types of things? I mean, are certain representations, do you understand the unramified representations, the tamely ramified representations, or does that exist, or are those silly questions to ask in some sense?
Well, all I can say about it is that I know that the types D, N, and R, he actually says what they are. R is for ramified. Those are the ramified ones. The N are non-ramified, and I don't remember what the D ones stand for.
You know the relation between the level and the conductor?
It's the same. That's
I see. Okay.
Yeah.
That's interesting.
Okay, are there any other questions? If not, let's thank Samuel again.